The hypervelocity ballistic threat. A single landing of the SpaceX Starship HLS will displace over 1,000 tons of lunar regolith at velocities exceeding 2 kilometers per second. This is not a simple dust cloud. It is a continuous sandblasting effect that launches razor-sharp basaltic shards at speeds that can shred hardware several kilometers away. The physics of plume surface interaction are no longer just a landing concern. They are a mission-ending threat for any nearby infrastructure. And the mechanics of this high-speed erosion start with the vacuum of the lunar surface. Vacuum expansion and plume focus. On Earth, atmospheric pressure constrains a rocket plume. On the Moon, the exhaust gas expands into a vacuum at Mach 10 or higher. This creates a focused jet of gas that scours the surface, entraining jagged regolith particles into a ballistic trajectory. Since there is no air to slow them down, these particles maintain their kinetic energy across the horizon. We are moving from the Apollo era, where small landers kicked up a nuisance, to the Artemis era, where multi-hundred-ton vehicles create a localized shotgun blast every time they touch down. This scale of erosion leads to a specific failure mode for nearby lunar hardware: structural pitting and optical degradation. Lunar regolith consists of glass shards and jagged basalt formed by eons of micrometeoroid impacts. When these shards hit a solar array or a habitat window at supersonic speeds, they do not just scratch the surface. They cause structural pitting and optical degradation. NASA testing at the Marshall Space Flight Center in early 2026 shows that even a 10-second exposure to high-velocity ejecta can reduce solar cell efficiency by 30% and compromise the pressure seals of docking ports. To prevent this, engineers are moving away from traditional landing legs toward chemical and thermal soil stabilization. Microwave sintering and pad construction. The most viable solution for the 2026 deployment phase is microwave sintering. By using a specialized rover to pulse high-frequency radiation into the regolith, we can melt the soil into a glass-like landing pad before the primary lander arrives. Another approach involves landing a dedicated robotic precursor that sprays a polymer binder to create a temporary crust. These methods are no longer theoretical. The autonomous sintering tests on the Viper 2 mission confirmed that lunar basalt can reach the required 1200 degrees Celsius with relatively low power inputs. But these engineering fixes reveal a deeper tension in the current lunar architecture: the real implication. The ejecta problem proves that lunar operations are now limited by site preparation rather than launch capacity. If a Starship cannot land within 500 meters of a base without sandblasting the solar arrays, the mission profile must shift from a single vehicle landing to a multi-stage construction sequence. This transition from exploring to civil engineering means that the first multi-ton payloads to the Moon will not be habitats, but the autonomous machines required to pave the way. For operators, this adds a 6 to 12-month lag between the first robotic landing and the first crewed arrival to allow for pad maturation. This changes the Artemis timeline from a race of rockets to a race of infrastructure. Watch the upcoming Icon technology demonstration in late 2026. If their sintering rate stays below 10 square meters per day, the Artemis 4 timeline will likely slip. The success of the lunar base depends entirely on the soil we prepare before we even arrive. Subscribe for more